Okay, welcome everybody for our Global Health Lecture Series tonight here at Pacific Science Center. My name is Brett, and I'll be your host and moderator tonight for this event. Just to give you a quick idea about formatting, we'll roughly have about a 55 minute lecture, after which we'll take a brief intermission, at which time that you guys can get more beverages or concessions if you would like, and then we'll come back together for questions and answers. Typically we're out of the space by about 8:30, if not 9 o'clock tonight. So just a reminder that every second Tuesday of every month, join Pacific Science Center for the Global Health and Development Lecture Series. This is part of the Science in the City program. These events highlight the amazing individuals and organizations in our region who are working on innovative, ambitious, and scalable solutions to address health problems that have a major impact in developing countries and possibly here at home. So thank you for joining us tonight. Just a reminder that if you are not a member with us, though tonight is free due to the generous donation from the Bill and Melinda, or I should say sponsorship from the Bill and Melinda Gates Foundation, if you're a member, all Science in the City events are free. So something to look into. If you do need to leave at any time, I ask that you actually do through the doors to your left instead of the doors that you came in through. Head outside and downstairs we need facilities. Concessions is just right out there as well. But when you come back, you will come back through those blue doors. Don't come back through the exit. And then tonight, because we do have alcohol on site, all of those drinks do need to be finished in the building and disposed of before you guys leave, so just don't take them home with you. So our next Global Health and Development series lecture is on October 9th at 7 p.m., and this will be featuring Dr. Peter Small, who currently leads the Global Health Institute at Stony Brook University, and I hear he is an expert in tuberculosis. So come back next month for another great talk. So it's my pleasure tonight to introduce you all to Dr. Emilio Emini for the talk on controlling the global HIV/AIDS epidemic. Where are we today? So Dr. Emini is currently director of the TB and HIV programs at the Bill and Melinda Gates Foundation. Prior to his current role, he served as senior vice president of vaccine research and development at Pfizer Incorporated, a position into which he transitioned subsequent to Pfizer's acquisition of Wyeth Pharmaceuticals in late 2009. At Wyeth, he led the R&D program that resulted in licensure of the Prevnar 13 vaccine for the prevention of the pneumococcal disease, as I stumble on that word. Dr. Emini joined the pharmaceutical industry in 1983 at the Merck Research Laboratories, where he led the biological research that resulted in the development of one of the first highly active antiretroviral therapies for the treatment of HIV infection. As head of vaccine research at Merck beginning in 1996, he led a number of vaccine research programs, including those that resulted in the licensure of the human papillomavirus and human rotavirus vaccines. So join me in welcoming Dr. Emini to the podium tonight.
Okay, great. Well, thank you, Brett, and thank you everybody for coming this evening. The last time I lectured to a group that rises up into the clouds like this one was when I used to do this at European universities, where if you've ever been to those lecture halls in European universities, they're actually much steeper than this, and it gets interesting. So my neck will crane for a while here. But thank you very much for coming. So, as Brett said, what I thought I'd talk to you about, discuss this evening is, as the title says here, is controlling the global HIV and AIDS epidemic, and where are we now, and where do we need to go? But when I was thinking about how to put together this talk, it's one of the truisms that you hear all the time is that it's difficult to figure out where you need to go and even where you are unless you don't recall where you came from. And it's important to remember where we came from with this epidemic. So, and given it's an eclectic crowd with a lot of different backgrounds, and I didn't want to make this a totally technical discussion, I thought let me take some time back and probably spend the first 20 minutes or so of the talk talking about the history of this epidemic, both in this country and globally as well. And for me, it was literally a trip down memory lane because, as you'll hear in a second, I was involved from the very beginning of the definition of the human immunodeficiency virus and working with the virus. And so there was a fair amount of history that I was capable of pulling back up again after all these years. So this, to a certain extent, is where it all started. Not biologically started, but where it was the first definition and the first recognition that we were dealing with a medical syndrome which was very unusual and somewhat unique. So this is the front page of the Morbidity and Mortality Weekly Report, the one that was published, as you can see up there, in July of 1981. And the Morbidity and Mortality Weekly Report, for those of you who are not familiar with it, is literally exactly what it says, right? It is a report that comes out every week from the Centers for Disease Control on the numbers of deaths and the numbers of reportable infectious diseases that occur, and what's associated in the previous week, and then what is associated, it makes for morbid reading, I'll be honest with you. But the interesting part of it is that there are articles that come out in it for new observations, and this was definitely a new observation. So what was reported here, as you can see at the title here, was two very rare medical conditions, Kaposi sarcoma and pneumocystis pneumonia, and we'll go through it in a second, as I said, among homosexual men in New York City and in California. And even though this was the first report, these were syndromes that were being seen among men in the MSM community in the big cities. You get some numbers occurring in New York, as you reported here. The other descriptions were from Los Angeles, but it was also being seen in San Francisco and some other cities. Now, what made this so unusual is that Kaposi sarcoma is a very rare tumor, typically tends to be expressed on the surface of the skin. I'll show you a picture of it in a second. And often, many times it's systemic. But it typically, prior to this time, was typically only seen among elderly men of Mediterranean origin in some countries in Europe. And in fact, it's not a particularly aggressive disease in those individuals. And somebody said, with Kaposi sarcoma, you don't die from Kaposi sarcoma, you die with Kaposi sarcoma, right? So it's typically in elderly men. But these were very aggressive cases of Kaposi sarcoma, leading rapidly to death. Even more interesting, if you want to use that terminology, was pneumocystis pneumonia. Pneumocystis is a fungal infection. And it's pretty much a given that if you're dealing with a fungal infection, and certainly one that causes pneumonia in this case, what immediately comes to mind is that you've got an immunodeficiency issue of some sort, all right? But what one had never seen before was something that appeared to be acquired because it was in young men. You typically would tend to see this, obviously, in older individuals, right? This is just a picture of Kaposi sarcoma. So it was very striking when it occurred. It was very aggressive, and so clearly there was something going on. I won't go through a lot of the details of what was being seen at the time, but we'll talk about the biology underlying the immunodeficiency of AIDS in a second. But the only point I wanted to make here was that it was evident very early on there were a number of diseases, mostly of an infectious disease nature, which were being seen, which were clearly associated with an immunodeficiency. And in fact, back in those days, before anyone really knew what was going on, you could actually stage the degree of the immunodeficiency by what was in fact being seen, right, in terms of that. So some of the first ones that were seen were things like thrush, which is, is a fungal infection of the mucosal membranes. Tuberculosis was probably one of the worst ones, and one of the ones that would tend to be seen earlier during the immunodeficiency course, and then you can see the rest very soft. Then there's pneumocystis, going all the way down to cytomegalovirus disease, and of the eye as a result of reactivation of endogenous cytomegalovirus. Very, very severe diseases. So what was going on? So I put up the picture here. For those of you who know the field can recognize this individual. This is Dr. Bob Gallo, who at the time was the head of the National Cancer, was a researcher, not the head. He was a researcher at the National Cancer Institute down at the NIH. Now Bob, and he's still scientifically active. He's now at the University of Maryland, and Bob actually, in the opinions of a lot of people, actually established the scientific base that ultimately led to the actual definition of the human immunodeficiency virus. A lot of people don't remember about Bob is that it was his laboratory that first identified a particular molecule called IL-2, which was very important for keeping T cells alive in cell culture. His laboratory was the first one to define that there were a particular class of viruses that are called the retroviruses that I'll describe to you in a second that were capable of infecting humans. A particular one called HTLV1, or human T-cell leukotropic virus type 1. He was the discoverer of this. So the concept that the causative agent, and I won't go through the details of why people began to think this, but the causative agent of what was this immunodeficiency that was being seen could be a virus that belonged to this particular class. To a large extent was made possible by, as I said, that sort of scientific environment and effort that Bob Gallo established. But in the end, he was not the one, and his laboratory was not the one that actually discovered the virus. So the virus, as you all know by now, is human immunodeficiency virus. Here is one of the very earliest micrographs of the virus. And the discoverers of the virus, as was eventually established, were Luc Montagnier and Françoise Barré-Sinoussi, both of whom won the Nobel Prize several years ago for the discovery of the virus. Now, for those of you who are familiar with the history of what was going on, it got a little bit ugly there for a while, back in the 1980s, between Bob Gallo's laboratory and the laboratory of Montagnier and Barré-Sinoussi at the Pasteur Institute, as to who was really responsible for the discovery of the virus. I won't go through all of that. It was an ugly set of events. Let's put it that way. But in the end, it's very clear that the actual discovery was from these two at the Pasteur Institute, and therefore the Nobel Prize was awarded to them. There are individuals who, of course, also believe that given the background and groundwork that Bob Gallo did, that he should have been awarded one as well, but that was not going to be the case. So this is the virus. This is a cartoon of it, and just want to make a couple of points about it. It is a envelope virus, so I'll see if the pointer works here. So it is literally what the envelope virus is. It's surrounded essentially by an envelope, a lipid membrane envelope, which is very important when we think about how this virus is transmitted, and we'll talk about it in a second. Has an internal core structure. And you see studded on its surface a set of proteins. These are actually a combination of carbohydrates and proteins, glycoprotein, that plays a very important role in defining the kind of cell that the virus actually infects. Now, just a couple of points about the virus. Because it is an envelope virus of this particular class and this particular structure, it is not an environmentally stable virus, right? Which we can all declare that it was lucky that which was the case. It's not a virus that can be transmitted by aerosol. It's not a virus that can be transmitted by survival on surfaces. It just simply won't survive, right? So the way in which this particular class of viruses, and there are other similar classes that are transmitted the same way, is transmitted by direct person-to-person contact through bodily fluids, right? So that pretty much limits the means of transmission, right? And it limits the means of transmission through sexual contact and largely through blood or blood products, right? So that's how it's transmitted. So when this virus was first, when the syndrome, which became known as AIDS, was first being defined, it was seen in populations of men who have sex with men, all right? It was seen among some heterosexual populations. Interestingly enough, back then it was also seen in hemophiliacs, right? And when we think about clotting factors and where they were produced from, before anybody knew that this needed to be screened out of the blood supply, that makes sense. Right? And also among populations of Haitians. That was the one that no one could actually figure out, all right? And now we know why, and I'll describe it to you in a second, but that's the syndrome that was observed, and those were the populations in which it was observed. Now, the virus turned out to be what's known as a retrovirus. So don't have to read the words, just look at the pictures. So, as you know, your genetic information is primarily in the form of DNA, right? And as you've all probably learned at some point in high school, you go from DNA to RNA to proteins, right? Retroviruses do it the other way around, largely, right? Their genetic information is in the form of RNA, right? And on infection, so here's the HIV-1 virus, human immunodeficiency virus, type 1. The two types were eventually discovered, but right now type 1 is the critical, important one. So these glycoproteins on the surface of the virus will bind to a particular receptor on the cell surface, actually to two receptors, but primary one is this one here, which is called a CD4 receptor, which I'll come back and tell you about that in a second. The envelope then fuses. The internal contents of the virus gets injected into the cytoplasm of the cell, what you see here in orange. And then in the process after that, the viral RNA gets reverse transcribed into DNA, all right? And therefore the reverse transcription process. And the DNA then makes its way into the nucleus of the cell, and the viral DNA then integrates itself into the whole cell DNA. It literally becomes part of the cell. genetically becomes part of the cell, right? And then ultimately when it's expressed, the viral DNA here in red, then it gets transcribed in the positive direction into RNA, which then makes the different protein constituents of the viral particle, and then the viral particle assembles itself and runs off the plasma membrane of the cell, and it takes off to start a new infection cycle in another cell. So a couple of take-home messages here. First one, and almost the most important one, is the CD4 receptor. This is the primary receptor that the virus uses to say, this is a cell I'm going to infect. And actually, when one considers the biochemistry of the virus, it's a fascinating story that if anyone's interested in, we can talk about later, in terms of why the virus, in fact, picked the CD4 receptor to a certain extent to infect the cell. Now, the important point to remember about a CD4 receptor is that the CD4 receptor, the CD4 molecule, actually is a marker of a very important cell, known, interestingly enough, as a CD4 cell, right? And these CD4 cells are T cells that are your central coordinating cells of your immune response. We'll put it that way. Now, it's a lot more complicated than that. But to make a long story short, no CD4 cells, no immune response. Basically, that's what it comes down to. So you can imagine that a virus that can infect the CD4 cell specifically, and as a result of the virus replication cycle I just showed you, result in the death of that cell, either directly by the virus or even almost ironically by the immune response to the virus-infected cell that actually even eliminates these cells. CD4 cells are eventually eliminated, and therefore what happens when that happens, of course, is that you wind up with an immunodeficiency, an acquired immunodeficiency because it was acquired as a result of the virus infection. The second thing to remember from this is this process of integration when the viral DNA becomes incorporated into the host cell DNA. Right? A manifestation of how your immune system actually works, of all of our immune systems work, is that these CD4 positive T cells can in fact go dormant. Right? Because, as an example, if you have an influenza virus infection and your immune system turns itself on and gets rid of the influenza virus, typically you won't get reinfected by the same strain of influenza virus. And that's because, as a result of that immune response to influenza virus, you establish an immunological memory. That immunological memory is to a very large extent due to CD4 cells that were specifically turned on in response to the influenza virus infection, and then they go dormant. But when they go dormant and they happen to be HIV infected and have incorporated the HIV DNA into its genetic information, the immune system doesn't recognize it as an infected cell because the DNA of the virus has essentially become part of the DNA of the cell. And CD4 positive T cells, when they become memory cells and go dormant, can actually persist for 10, 20, 30, 40 years, particularly in many cases for the lifetime of an individual. So what this means is that the virus, once it establishes an infection in an individual, in fact, stays with that individual and can stay with the individual and does stay with the individual, unfortunately, for the life of the individual. Right? Which is why, at this stage, at least, no one has yet figured out how to cure an HIV infection. We can keep it under control, and I'll discuss that a little bit later, but no one knows how to cure it, right? And that's the reason why. Okay? All right, so this is a very old schematic. This goes back into the late 1980s, but it's still valid today, and it shows the course of the infection versus the course of the disease. So what's plotted here is in red are the number of HIV particles, the number of circulating viruses that one can measure in the blood of an infected individual. And in blue, we have the CD4 cell count of the individual, right? So, and just look at the time frame that we have here. So in someone who was untreated, right? So this was, before there were any treatments for controlling HIV infection, someone who's untreated. Typically, after infection occurred, a few weeks later, all of a sudden you see what's called the acute phase of virus infection, right? So you get a very high virus load of virus within the individual. You see how the red line peaks up, all right? CD4 cells begin to decline rapidly because they're being killed by the virus. But in spite of this, all right, the immune system actually works, right? And what it does is that it recognizes that you got an infection, so the immune system turns itself on to knock down the infection, which it does, okay? And even in spite of the fact that the CD4 cell count took a hit, so the virus levels come down, but they don't go away entirely. They still exist at a very high measurable level that continues to persist over time. This can vary by 100-fold depending on an individual. And over time, which can be many years, all right, at least many months, but certainly in many cases for many years, the CD4 cell counts do decline. Right? One of the interesting things about the immune system is that the immune system is incredibly resilient. These CD4 cells will replenish themselves, and they will continuously turn over and continuously replenish themselves. The virus continuously turns over. A virus infects, kills the cells, CD4 cells come right back, and so you get this constant battle going on between replenishing CD4 cells, an immune system trying to keep the virus under control, a virus staying one step ahead of the CD4 cells, of the immune system response to it, and this is what goes on for many years. In an individual who, as we say now, is living with HIV. Right? And then ultimately, the immune system can no longer keep up with it, and eventually the number of CD4 cells crashes down, virus levels come up, and this is the syndrome that's known as the Acquired Immunodeficiency Syndrome. Right? It's a syndrome that occurs at the end stage of the disease, where you see all of the other opportunistic infections that we were talking about a moment ago. Right? Because at that point, your immune system just simply can't deal with standard infections that are out there, whether it be tuberculosis or cystic pneumonia, things of that nature. Right? So, I'm going to scatter some statistics throughout the talk here. So these are data from 2016. They're a couple of years old, but CDC numbers tend to be a couple of years old when they come out. And this is pretty striking data. So since the epidemic began, and it was at least first recognized in the early 1980s, all right, in this country alone, about 1.3 million people, all right, have actually received an AIDS diagnosis. Now, this is not the number of people who live with the virus. This is the number of people who actually went to the end stage of the disease and actually had an AIDS diagnosis. And roughly half of those individuals, about 500,000, have died. Right? Now, the reason why they haven't all died was because there were individuals who were still alive, even in late stages of the disease, when the therapies that I'll describe to you in a second became available. Right? But for those individuals, unfortunately, who were in the late stages of the disease, because before highly active therapies became available, unfortunately, they died. Right? This is, in fact, a terminal infection. So how many, I don't know, how many of you have ever seen or ever heard of the Quilt Project? I'm sure some of you may have, yeah, I'm not sure. So this was a project that got started in the late 1980s. And the purpose of the Quilt Project was to actually sew quilts that reflected the lives and celebrated the lives of individuals who died as a result of AIDS. And each one of these panels, as you see, contains the panel is about this size here. It contains about 4 to 6 individual panels reflecting 4 to 6 individuals who died. Now, the interesting thing about this Quilt Project that I found very, very striking is that for many people, when numbers are numbers, right? And when one starts talking about big numbers like 1.2 million people or 500,000 people dying, it's very difficult to get your head around it. This was an event that occurred in the early 1990s on the Washington Mall in Washington, D.C., where all of the quilts that have been sewn to date reflective of individuals who have suffered from AIDS and died from AIDS were laid out on the Washington Mall between the Capitol and the Lincoln Memorial. And when you take a look at the picture, it was actually striking. I mean, it covered the entire mall. Right? I was there on that day, and it was just an extraordinary experience. But this is what really gives you a sense of the nature of the epidemic and the degree of concern that it was caused certainly among populations that were suffering from the infection and in general, obviously, as well. So what are the current statistics globally? So again, as of 2017, these are statistics from UNAIDS. UNAIDS is the UN organization that's responsible for coordinating the global AIDS response. So since the start of the epidemic, it's estimated that over 77 million people, right, have been infected with the virus globally. These are worldwide numbers. Right? This is probably an underestimate because numbers didn't start to be counted until the mid-1990s globally. So it's probably larger than that, but we'll say it's about 77 million people, almost 80 million people became infected with the virus, and about 35, 36 million people have died as a result of AIDS globally. This is a real epidemic, right? and continues to be a real epidemic, as you'll see in a second. This is another striking picture. So this is an aerial photograph of a cemetery in Central Africa, in Uganda, and these are all freshly dug graves. At the height of the epidemic, this is how rapidly people were dying from AIDS. Right? to the point where you would actually have all of these fields of these freshly dug graves. I was in Kampala at the time and spent a few days in Kampala. And as you drove from the airport in Entebbe into Kampala, what lined the roads were coffin makers. I mean, and they were literally, one right after the other, because that's how rapidly coffins were being used, and this is how rapidly people were being buried. Right? And it gives you another sense of the extent of the epidemic that was going on and how devastating it was. So in 2016, I'm going to show you a number of maps like this with colors on them. So this is a reflection of the number of people living with HIV. Now, you have to be a little bit careful when you look at this particular graphic, because you've got countries like, for instance, like India, that apparently have a fairly large number of individuals living with HIV, certainly here in Southern Africa, a fair number in the US. These are absolute numbers, right? I'll show you a little bit later the proportional numbers, which are a better reflection as to where the epidemic actually is right now. But obviously India's got a lot of people, so even though the proportion of infected individuals on a population basis is small, the absolute number is large, right? The only reason I wanted to show you this was to give you a sense that this remains a global epidemic, right? And as you'll see a little bit later, it's actually an ongoing, increasing epidemic in some parts of the world as well. So where did the virus come from? Right? And a lot of the work that was done over the last 25 years, 30 years, was also basic academic work trying to understand where the virus came from, and the nature of the epidemic. And the reason why I want to spend just a few minutes talking about this is that it addresses some of the early enigmas in trying to understand why certain populations were being infected with the virus. But also, it's a very good example of how a new biological entity comes to be, right, and how it can enter into a population, right? And these are problems that we have to keep very much in mind, because just as HIV made its appearance, within the last set of years, right, other viruses have made their appearances as well, right? So this makes for a fairly interesting story. So if you want to look at it that way. So where it all started was essentially here in West Africa, and pretty much in this region, bounded by Cameroon and the Democratic Republic of the Congo. There are several rivers that run here. Now, this is an area that is heavily populated by populations, and actually separate populations of chimpanzees. All right, and many of you already know the punchline here: the virus came from chimpanzees into humans. But one of the more interesting aspects of this, if you will, is how did the virus get into chimpanzees in the first place? The nature of the virus is such that it undergoes continuous genetic evolution, which we'll talk about in a second. So one can actually, if you've got the right samples, you can actually date the evolution of the virus back in time, because it occurs at a constant rate as the virus moves through the population, right? So the best guess is that the virus probably made its way into chimpanzees literally centuries ago, right? It can be dated back to the 15th and 16th century. All right? And where the chimpanzee picked it up because chimpanzees, certain chimpanzees, and most of the ones living in this part of Africa do so, have a tendency to every now and then they get a taste for meat. And the easiest meat for them to get a hold of and eat are monkeys. Right? And there are many different species of monkeys that live in this part of Africa, most of Africa for that matter, but certainly in this part of Africa. And these different species of monkeys, every single one of them, almost no exception, are infected with these kinds of retroviruses, right? They're actually called lentiviruses, a particular kind of retrovirus. They're infected with it. But the interesting thing about the monkeys is that they don't die and develop clinical disease as a result of being infected, even though they have very, very high virus titers. So what that tells you is that whenever it happened, that these species of monkeys became infected with the monkey version of the virus. So the monkey version of the virus won't infect humans. The monkey version of the virus. The monkeys and the viruses became adapted to each other. So through the process of evolution and natural selection, you wound up with a case where you have the virus and the monkeys living fairly happily with each other. Let's put it that way. Just like herpes viruses will live fairly happily with most humans these days, right? I mean, this goes way back to the start basically of the species. But what happened with the chimpanzee is that the viruses that infect the monkeys won't infect chimpanzees, won't infect humans. But there was one chimpanzee, one day, that decided to eat a monkey of one species and a monkey of another species, who knows, all right? And as a result, there was a recombination event that occurred within the chimpanzee of the viruses from the two different monkeys, winding up developing a new virus that now had the genetic capability and the biochemical capability of infecting the chimpanzee. right? There was a fortuitous chance event. So when did this happen? As I said, it happened probably several centuries ago. So during that time, the virus stayed and probably transmitted substantially in the chimpanzee population, but it didn't go anywhere beyond that point. At some point, it jumped into humans. Why did it jump into humans? It jumped into humans because a practice that occurs in this part of Africa is called bushmeat hunting, right? You go out and you hunt monkeys, you go out and you hunt chimpanzees, all right? And you sell it as bushmeat in the markets and you eat it. When you butcher the animal, there's a lot of blood and a lot of things of that nature, and eventually there was a transmission event that occurred from a chimpanzee into a human. The earliest known transmission event, because you've actually found the sample with the virus, dates back into probably the 1930s, 1920s, 1930s. It was a fairly early event, right? But it didn't go anywhere. It just stayed there. Why? Because what you were dealing here were essentially fairly isolated populations, right? Populations that didn't move around, right? But then what happened in the late 1950s and through the 1960s in Africa? Decolonization. And as a result of decolonization, particularly the decolonization of what's now known as the Democratic Republic of the Congo, this used to be known as the Belgian Congo. For those of you who read, I forget the name of the author, quickly. It's very famous now. But anyway, it was known as the Belgian Congo, and the capital of the Belgian Congo was Leopoldville, named after King Leopold of Belgium. As a result of that decolonization, there were massive movements of people into the big cities, right? And particularly from the rural areas into the big cities. This is a virus that's sexually transmitted, so you can imagine that there was movement that occurred. It took a hold in the big cities, right? And interestingly enough, as a result, as part of that decolonization event, and this was a French-speaking part of Africa, both Belgian, French, and Portuguese-speaking part of Africa, as what is now known as the DRC, the Democratic Republic of Congo, became independent back then, they needed workers that, because essentially all the Belgians have left. They needed workers to manage their administrative activities, and where did the workers come from? They actually came from Haiti. And very large numbers of them immigrated back to Haiti, and then eventually a number of them came back from then to Haiti. The virus then transmitted into Haiti, and then from Haiti it entered into the populations here in the US. And the rest is history, and it made its way around. Right? The transmission of the virus in Africa actually occurred a number of years later as a result mostly of mining activities in Africa. Right? And large groups of men, in order to make a living, would travel as groups to work in the mines, primarily in the mines of southern and eastern Africa. Right? And in fact, one could actually trace the virus and how it evolved as it made its way down the railroad lines from West Africa down into southern Africa, over to East Africa, and then back down into southern Africa. Okay? And before anybody really understood what was going on, we wound up with a massive epidemic and a massive transmission. So, and those led to the numbers that we talked about a moment ago. Back in this country, when it became clear that we were dealing with a very significant epidemic, it started a movement, right? As is very typical for these kinds of things, politicians were not particularly on top of things to recognize that we were dealing with a significant issue here. The amount of effort and time that was required, the amount of effort and money that needed to actually be put in to try to deal with what are we dealing with here, how can we potentially treat it, how can we potentially cure it, can we develop a vaccine, all of the things that one typically does with an infectious disease took a while to get going, right? And a fair amount of it was driven as a result of the activist community, mostly activist communities of MSNs, who really pushed very hard to the government to say, we need to do something. This is me, actually, before I grew a beard, and I was also much younger, yeah. So at the time, I was working at the Merck Research Laboratories. I was a trained virologist. I'm actually, a lot of my colleagues who are here from the Gates Foundation don't know this. I'm actually a trained poliovirologist. And actually, even before then, I used to work with viruses which were transmitted by mosquitoes. But so while I was at the Merck Research Laboratories, it became clear back in those days, many pharmaceutical companies got together and said, this is something we need to do something about. I happened to be the only real virologist at Merck at the time, so I became the founding director of the Department of Antiviral Research, and that's how I got involved in all of this. You can tell I was a much more serious individual in those days. So I'm just going to show you the titles of several scientific publications that we were involved in, but each one of these actually turned out to be fairly insignificant in trying to understand what we were dealing with the virus. Because we knew what the class of virus was, we pretty much knew biochemically where we could actually attack the virus. So one of the first drugs that we developed was this drug that, as you can see, never made it to final development because it had only a number associated with it, L697661. Which was a drug that actually prevented the reverse transcription event. If the virus can't take its RNA and turn it into DNA, it doesn't go anywhere, it's done. We brought this forward into a clinical study, but what happened is that what we learned when we brought it forward in a clinical study is that essentially the drug was only effective for literally 2 days. Virus levels dropped, and then the virus came right back up again. And what we discovered as a result of that rapid turnaround, well, what we discovered was that what came back up again was resistant virus that was no longer susceptible to the drug. I remember my boss at the time, who was the head of the research laboratories, essentially told me I was a fool, that this couldn't possibly be the case. When you think about it, for 48 hours, an infected individual, the virus population became infected. I said, no, this is in fact what happened. And what we learned as a result of this study was that in fact the virus population in infected individuals turns over incredibly rapidly. All right? And when you think about it, it's because your CD4 cells turn over incredibly rapidly. Right? And as a result of that, and because the other thing about the virus is that the reverse transcription event that I was referring to, going from RNA to DNA, is an error-prone event. Right? So it's got 10,000 bases. That's how long the genetic information of the virus is. Right? And it actually misincorporates a base every 10,000 times. So when you think about it, there's a reason for that, because if it's more than that, the virus would evolve itself out of existence, right? Because most of those changes are lethal changes. Okay? So that limits the size of the genome, as they say, limits how many genetic changes you can put. So the virus actually pushed it all the way to the edge. So when you think about it, when you've got literally many copies, literally, as it turned out when we discovered this, billions of copies of circulating virus, within any infected individual at any time, there are at least 10 to 100 copies of the virus that are already resistant to whatever single drug you throw at it. And therefore very rapidly turns over, and you very rapidly select for resistance. And we learned this by using this particular drug, but which unfortunately we didn't know what to do with at that moment. Then we developed this other drug, which again, called L73724. This one was actually successfully developed. This was an inhibitor of an enzyme of the virus known as the protease, which the virus needs to mature itself as it does out from the cell. This is a very potent drug. Right? And at this time, there had been a number of additional drugs that had been developed that were reverse transcriptase preventing drugs that hit the reverse transcriptase in different ways. Right? We had developed this protease inhibitor. And we knew that the virus could become resistant to the reverse transcriptase drugs at a rate of 1 in 10,000. All right? And this one was also at a rate of 1 in 10,000, a little bit less, but roughly at a rate of 1 in 10,000. Okay? So 10,000 in log terminology is 10 to the 4, right? 10, 100, 1,000, 10,000. 10,000 is 10 to the 4. So we reasoned that if you could take 3 drugs and use them simultaneously together in an individual who hadn't seen any of those 3 drugs at the same time, the probability that you would have a pre-existing resistant virus would be 10 to the 4 times 10 to the 4 times 10 to the 4, right? Which then essentially puts you up at 10 to the 12, which is a very big number. And we knew that the total body amount of an individual who's infected and not previously treated was on the order of 10 to the 10, all right? So therefore we said, let's try 3 drugs at one time and see what kind of effect it would have. And to make a long story short, this was the clinical study that we reported in the New England Journal that actually showed if you use the 3 drugs together, you could actually suppress the virus load within the individual and keep it suppressed without selecting for resistant virus. Well, the trick was, of course, is that you had to keep giving the drugs, right? You couldn't stop, because if you stopped, the virus loads would come right back, and that still is the case today, right? And in many years since then, we've now developed easier ways with different classes of drugs to do this, where essentially right now we're at a point where it is 1 pill of 3 drugs once a day. That wasn't the case back here. Back in these days, there was multiple pills twice a day, and it was very complicated. So in order to get to the point where you got to treat somebody for 10, 20, 30, 40 years, 1 pill once a day was where you needed to be, and that's where we are now. As a matter of fact, one of the drugs that is commonly used in Africa is this drug here that came out of my laboratory. This is the drug that eventually became known as efavirenz, right, which was a very commonly used drug and a very potent drug as a reverse transcriptase inhibitor of the virus. So when these drugs became available and these therapies became available, these triple combination drug combinations and what are known as highly active antiretroviral therapy really finally became licensed in roughly 1995. That was actually 1996. Now, one of the striking things is that in this part of the world, where these drugs could be made available and could be afforded, so to speak, both by many people didn't have to pay for their own drugs; they were actually made available, but only in this part of the world. Prior to the availability of these drugs, what you had in the hospitals in the big cities in New York and what have you, you had AIDS wards, right? Where people who had, terminal cases of AIDS were literally going to die, right? Those AIDS wards closed down literally overnight. In 4 weeks, every AIDS ward in the city of New York closed down. And that's because as soon as you started them on this therapy, you didn't die anymore. Virus loads dropped. Now, some individuals, unfortunately, it's too late. Okay? But eventually, and certainly as the therapies became easier to take, it became easier to keep those under control. But that was only in this part of the world. It was only in Europe. It's not the case in other parts of the world. It's certainly not the case in Africa. So what made the big difference in Africa was this program. Right? This was a program that got started under President George W. Bush, right? Which is called the President's Emergency Program for AIDS Relief. And what the objective here is let's make these drugs available to everybody around the world, not just in Africa, but everybody around the world, in lower and middle income countries who need the drugs. This is a big program because it's not just simply a matter of making the drugs available. You actually have to deliver the drugs. You've got to get it to the patients. You've got to find people who are HIV infected. You've got to keep them on therapy. So what this program did was to build the medical infrastructure in many countries that didn't have a medical infrastructure, right, in order to be able to deliver the drugs. As a matter of fact, it's almost unfortunately silly to say, but the reality is you got better medical care if you had AIDS than if you didn't, if you were living with HIV if you didn't have it, right? Simply because you became part of the system, right, which was designed specifically to deliver HIV-related drugs, but was working obviously for medical care in general, right? And this was entirely driven by this, which continues to this day. This is a $6 billion a year program. This is not trivial. This is a big program, which has now been going on since the mid-2000s. Right? So we're 15 years almost into this program. So here you can see the impact of this. So if you take a look here, this is the number of HIV and AIDS deaths that have been averted as a result of antiretroviral therapy. These are pretty solid numbers. So what you see here, these are the number of deaths. And these are the number of deaths that would continue to have occurred as we made our way, and these are pretty conservative numbers, as we made our way from 2000 to 2016. But as soon as the PEPFAR program started going in earnest, which as I said was in the mid-2000s, the number of deaths just started to drop. The number of deaths dropped, so in orange you see the number of calculated deaths that have been averted as a result of this program and making it available. Now the number of people living with HIV has gone up, and it's gone up because you don't die anymore. Right? So the number of people living with the virus goes up, but these are people that you have to keep on therapy. Right? So another, and this extremely important result, as an extremely important consequence of the work that was done and of the PEPFAR program, and we didn't talk about this before, is that another way that became very clear, and this was work that was done by a number of individuals, mostly from Amsterdam, working in Africa. The virus was being transmitted also from mother to child. And in this part of the world, mother to infant transmission turned out to be a very common means of transmission. Right? Infection occurred actually during the process of birth. All right? It was an intrapartum infection that occurred. Right? And it also occurred as a result of breastfeeding. There was plenty of virus in the breast milk of mothers who were infected with the virus, and eventually the baby became infected. Learning how to prevent infection transmission from mother to child was one of the biggest advances in the field that occurred during these last 25 years. Right? And part of it is finding, right now, mothers who go into antenatal clinics in many parts of the world are automatically tested for HIV. If they're HIV positive, they are placed on a specific combination of drugs for HIV therapy to lower the virus loads, and then when the babies are born, they're put on a period of HIV therapy as well. Right? It has been incredibly effective. Right? And as a result, as a result of that, what you saw here in this slide are the number of cases have been averted, number of cases prevented of mother-to-child transmission. And particularly where you have the highest burden of HIV infection in Southern and Eastern Africa, the numbers of related infections have been extraordinary, all right? As a result of developing the means of how to do that and making it available largely through the PEPFAR program into these populations. In this country, mother-to-child transmission is essentially zero. It's done. Don't see it anymore, simply because you can find it and you can deal with it. All right. So let's go back to the global HIV statistics. As I said, so today, again, this is late 2017, the last set of numbers that are available, but they're fairly recent. Number of people globally living with HIV, as you can see, is about 37 million. 22 million people of those 37 million are now accessing antiretroviral therapy, as it's called, anti-HIV therapy, and living with the virus as a result of, and surviving as a result of it. But in spite of that, and I will talk about the future, the third statistic here is the one that bothers all of us. We still have 1.8 million new infections a year. It's still a very, very large number. Now, when you think about it, right, 22 million out of 37 million, that leaves about a third of the population, right, that needs therapy, not accessing therapy, either because we don't know that they're infected or because they're just simply not accessing it for any one of a number of different reasons, right? And 1.8 million new infections. And even, here we are in 2017, and these highly active antiretroviral therapies became available in 1996, all right? We're still at a point where we have, unfortunately, about 1 million people a year still dying from AIDS-related illnesses globally. All right. In the United States, and again, these numbers are a little bit old, 2015, but they give you a reflection of what's going on. So we've got about 1 million people living with HIV, all pretty much under highly active antiretroviral therapy. But look at the numbers, right? We're still dealing with as many as 38,000. Numbers are going down slowly, but they're very slow right now. So the current estimate is that last year there were about 35,000 new infections, still in the United States alone. Okay? And so we're doing certainly much better than we were doing back in the late 1980s and early 1990s, but there's still a lot of room to move here. So this is the share of the population. So this now looks at the proportion of individuals in different countries who are living with the virus. So it gives you a better sense of where the epidemic is. And as you can see, most of it is centered in Southern and Eastern Africa. One of the reasons why that's the case is that in these countries, it took a while for the countries to recognize that they were dealing with a significant problem, right? So, and a lot of it were, again, mostly populations of young men living in groups, going to work for many months in the mines, the diamond mines and the gold mines. That's how South Africa had its start, back in this part of Africa. So you can imagine a fair amount of sexual transmission that then comes back into the individual populations. But, the United States still has a fair number of new infections that occur mostly in marginalized populations that can occur as a result of IV drug abuse. The opioid epidemic has helped situations a lot. There was an outbreak in southern Indiana 2 years ago as a result of primarily IV drug abuse, as a result of the opioid epidemic that occurred there. The other place to watch is Russia. Mostly IV drug abuse in Russia, a very significant issue, and particularly in central Russia, again, it's opioid abuse that goes on in that part of the world. This part of the world is mostly sexual transmission. The death rates reflect the infection rates. So of those 1.8 million, of the roughly 1 million deaths that occur every year, it's again mostly in southern and eastern Africa. Right? And here are the annual numbers of new infections, and those new infections are again occurring in southern Africa and eastern Africa. And you'll see Nigeria here in Western Africa is a pretty significant. And these are absolute numbers. So again, India proportionately is small, but it's a big population, right? So the absolute numbers tend to be large. So I'm going to conclude with a series of slides to talk about. All right, so we have challenges, and the challenges are 1.8 million new infections a year. It's not trivial. That's a big number, right? So what do we need to do here? Now, here's the concern, and this is true of any epidemic, and it's not any different for HIV. The big concern is that in spite of all of the successes that we've had over the last 25 years in attempting to control this epidemic, the reality is, if you're not careful, it will come right back. Right? And I'll tell you why. So what are the challenges that we face and what do we need to do? So one of the biggest challenges are that we're missing two of the most important biomedical interventions one needs to have to control any kind of infectious disease epidemic. There's no vaccine, right? And there's no cure. We talked about why there's no cure, right? You can keep the virus under control, but you can't eliminate it from an individual who's already been living with the virus. So if you stop the therapy, all right, or if the virus for some reason becomes resistant because the individual is not adhering to therapy appropriately, right, those virus levels will come right back up again within the individual, and you can transmit. One thing about individuals who are fully suppressed, the virus levels are very low within the individual as a result of therapy. And this is very important, those individuals won't transmit. Right? There isn't sufficient virus in those individuals to transmit, right? Which is really good because that's how you can keep the epidemic to a certain extent under control. But you've got to keep those individuals under treatment, right? But you can't cure it, right? So that's a problem. And there is no vaccine. And one of the reasons why there's no vaccine is that this virus has developed a set of structures on its surface that essentially allows it to avoid your typical immune responses to the virus itself. And just as I said, the virus can genetically change, in response to drugs. It genetically changes in response to your immune response to the virus, right? So that normal, for instance, antibody responses that would normally develop to neutralize the virus stays one step ahead of it, right? And it constantly changes. Right? So how do you develop a vaccine against something that's always changing? Right? It's bad enough for flu, where you got to change the vaccine every year. Here you would have to change it every couple of minutes. I mean, it moves that quickly, okay? So therefore, there is no vaccine. Not that anybody's given up trying to develop a vaccine. That's still needed, all right? And we know a lot of us continue to work on this, but it's going to be a big challenge. But anyway, at the moment, those biomedical interventions don't occur. The other thing is that in many parts of the world where the virus is transmitting, as I put it here, that it's a challenging epidemic and HIV transmission characteristics, right? What I mean by that is this is primarily sexual transmission, right, that occurs. And we'll talk about, I'll show you some slides here to talk about the social and demographic drivers of HIV exposure. So this goes back to an earlier slide that I showed you. Here are the annual numbers of new HIV infections that occur, right? So, and you can see that many of these large numbers are in southern and eastern Africa, some basically in Western Africa. Now, this is an important slide because if you take a look at across many countries and you take a look at the share of the infection, if you will, comparing the share of men living with HIV and the share of women, what does one see? You come off the diagonal, right? There are many of these countries, and these are your southern and eastern African countries, South Africa, Botswana, Lesotho, Zimbabwe, Zambia, Kenya, etc., right? The proportion of women who are living with the virus is higher than the proportion of men living with the virus. So this immediately starts giving you a sense in terms of where a lot of this transmission is actually occurring. And the current hypothesis is that basically this is what happens, and this is work that's been done by investigators down in South Africa, where essentially you've got populations of older women, if you will, that's called mean age is about 26 years of age, who are living with the virus, unfortunately, right? These women will transmit the virus to men. These are men who, again, primarily make use of, female sex workers, or there's a lot of transactional sex that occurs, which is very unfortunate as a result of the social conditions in these countries. The men become infected, but then they transmit the virus to younger women, all right? And these younger women are very young women. These are typically adolescent girls and young women, right, who are very vulnerable, unfortunately, to sexual exploitation, and also in which engage transactional sex. There is no money to live, right? There is no money to get the things that you want to get. And the best way to get that money is to establish a sexual relationship with somebody who just made money working in a mine, right? And it comes back. So this, as you can imagine, establishes a rather vicious cycle. And this is the cycle that we basically have to deal with. And in fact, these numbers are striking, because every week, every 7 days, it's estimated that 7,000 young women, between 15 and 24 years of age, worldwide become infected with the virus. Right? That in and of itself is an extraordinary number. In sub-Saharan Africa, 3 or 4 new infections occurs in these 15 to 19-year-old women, and young women between 15 and 24 years of age are twice as likely to be living with the virus than men are. Right? This is a highly vulnerable population, right? Simply as a result of very social demographic factors, which are difficult to deal with. There's an additional demographic factor, and that is, when does primary sexual transmission occur? It occurs, as you can tell, in these young populations. Slightly older men, but they're still in their 20s, and young women of this particular age. So one of the things that we see in southern and eastern African countries, and these are data from Zambia, I believe, yeah, these are data from Zambia, is what's called the demographic bulge. And what does that refer to? What that refers to is that if you go back to 1990, this is the distribution of people by age, right? So the younger you are, you have more. And here we're looking both at, men and these are women in red and men in blue. But you take typical distribution, and as you get older, the number of individuals drops off because you die from a number of different cases. But one of the things that has happened from a public health perspective through the 1990s and the 2000s is that a lot of the reasons why young babies died have pretty much gone away. And why? Because of vaccination programs. Vaccination programs against standard diseases. Measles, right? Very big one. Polio, obviously, for many, many years. Diphtheria, tetanus, pertussis, right? So as a result, these are all very young countries, right? People who were born from the late 90s to the 2000s, right, were actually living for a lot longer than they would have, going back to the 1990s. Therefore, for many of these countries, we joke about it. You go to Zambia, you go to Zimbabwe, a little bit less in South Africa, but you go to Zambia, Zimbabwe, countries of that nature. When I get off the plane, I'm the oldest person in the country. I mean, it's not bad. I mean, seriously, you walk down the street and everybody's 18, 19 years old. Here I am, 60, right? 4. So it's coming at 65. So at any rate, so you got, but what's the issue here? The issue is that these are populations that will grow into that adolescent population, right? And that's where you get maximal sexual transmission, right? And so therefore the substrate, if you will, for new infections is very large. So if you can't control the new infections that occur, particularly among young women and young men, at that particular age range, you can imagine we can easily be, if we don't get those numbers down lower of new infections, 15 years from now, in terms of absolute numbers of people living with HIV, we could be actually worse off than we were 15 years ago. Right? So these are the kinds of things that one needs to be very careful of when one tries to control an epidemic. It can get away from you for any one of a number of reasons. So I mentioned the third one down, which is there are challenges with achieving and maintaining viral suppressive treatment. What do I mean by that? You can't cure, but viral suppressive treatment requires continuous administration of the drug, right? Even if it's one pill once a day, it's not that you're treating somebody for a few days. I mean, think how difficult it is for anybody in this room to take a 7-day course of antibiotics, right? If you wind up with an ear infection. Here we're talking for the rest of one's life, right? So these are difficulties that one faces, for the next 20, 30, 40 years. So not only are there individual support issues that we have to build into place, but you have to have the systems in place, the delivery systems in place that allows you to do it, and that allows you to do it in a way that makes, unfortunately, economic sense as well. So that becomes important. So we need definitely to improve the ability to find people living with the virus and simplify the delivery of lifelong treatment. These are all programs that my group at the foundation is working on very and supports to figure out how to do this. Another problem or challenges with programs to prevent HIV acquisition. So you can say, well, why don't you tell people what you need to do to prevent acquisition? Well, you can imagine how difficult that is, right? And particularly in many of these populations, the concept of being HIV infected is still very highly stigmatized, right? And so people prefer not to talk about it. And people, so the only reason we can find people living with the virus is because they're automatically tested when they show up at a clinic or when they show up at an neonatal clinic if it's a woman who's expecting. But the reality is, typically it's a challenge to get men who are living with the virus and getting them tested and therefore getting them on treatment as a result of it. And when you start talking about prevention, I mean, there is oral PrEP, right? As many of you may be aware, it's one pill once a day that you can take to prevent acquisition of HIV infection, and it's very heavily used in many populations in the big cities in this country, but it's very difficult in these populations, right? Because as soon as you say, yes, I'm going to take oral PrEP to prevent HIV acquisition, you're essentially stigmatized. And a lot of it is self-stigmatization, which is what will people think of me? What will my partner think of me, And you don't want to lose those social connections, and that's and so this is not a trivial issue, but it's something that we do need to work on because short of a vaccine, there are a number of biochemical prevention methods that are being developed, but the challenge is going to be to actually not only deliver them, but to get them accepted. And then finally, and my slide died on me, and it's not working anymore. But if you can read the gray bottom at the bottom line is, this is interesting. When it's okay, it's the last slide anyway. It's the last slide. Leave it alone. What it says there at the bottom is that there are insufficient and stagnating global responses. So when we take a look at everything that still needs to be done, developing a vaccine that's yet to be developed and all the research that's required in there, developing new biochemical prevention methods, getting them delivered, simplifying how we deliver treatment right now and all of that, and you take a look at the money that the world throws at this, it doesn't take much to figure out it's insufficient. Right? But unfortunately, we're living at a time when the global response money has pretty much stagnated. So we can say the PEPFAR funds are $6 billion a year. We need more than $6 billion a year really do this the right way. And the concern is once those numbers flatten, they tend to drift downwards, right? And that's not the way in which we need to be as gathers. So driving the efforts to and the advocacy that's needed to make sure that the funding remains in place is very much needed, because the concern is we'll lose control of the epidemic. And again, just to reiterate, if you model this out, we can easily be worse off 15 years from now than we were 15 years ago if we don't watch it carefully. So that's it. So thank you very much, and I think after we take a break, we can take some questions if anybody wants to hang around. So that's right. Thank you very much for your attention.
That was really loud, sorry. We're going to go ahead and get the discussion going. So at this time, I'll ask that you guys raise your hands, and then Dr. E, as we're now calling him, will call on you and answer your questions. I can't pronounce the last name for some reason. I'm sick, I'm sorry. So at this time, raise your hands. He'll answer. I just want to remind him, please repeat the questions, because we can hear you guys, though you guys can't hear each other that well. So go ahead and ask some great questions.
I have a question about the vaccine.
Yes.
So with all the mutations, what do you, like, this is really an intense question, but do you think a vaccine will ever be made? Like, what are people trying to do, given the
That's a good question. So actually, this goes back to the question, I got the question, my apologies. The question relates to the fact is, do I believe, now believe is an interesting word, right? But do I believe that a vaccine will ever be made? And really the underlying question is, what are the challenges, right?
Well, like, what are people actually,
what are people actually trying to do? Okay, so a couple of things are going on right now. So there is, remember I told you earlier about a related virus that infects monkeys, right? So that related virus is known as the simian immunodeficiency virus. And so the simian immunodeficiency virus infections of monkeys have been used to test different potential vaccine approaches, right? So can we prevent a monkey from being infected with SIV in the laboratory, and can those approaches work for HIV in humans? There is one approach in which it appears that it can consistently establish an immune response that will prevent infection of monkeys by SIV. Now, here's the challenge with that one. No one really knows what that immune response actually is. Now, typically in the field of work I'm in, is if you don't know what it is, it's probably not real, okay? But you just don't know, right? But this is such a significant problem that the decision was made by both the NIH and the foundation is contributing to this as well, to do the study of the equivalent vaccine in humans. What is real at this point, right? It's a safe approach, and the question is, will it have an impact in humans? That study started last year. Results will be available in about the next 4 years or so. Okay, these are high incidence populations, obviously, like in southern and eastern Africa, where you do it. Another approach was an approach where it was a vaccine approach that was done in Thailand a number of years ago. It's called the RB144 study, in which it appeared that vaccine elicited an immune response that had some protective effect, very low, about roughly 30 to 50%, depending on how you cut the numbers. I think it's more like 30%. The bottom line is, again, the nature of the immune response that may have been responsible for that is unclear, right? But we developed a version of the vaccine that should be effective if that result is real in populations in southern Africa. That's currently in clinical study as well. Again, we'll see results in the next few years. The reason why you hear hesitancy in my voice is because it literally is an experiment. We have to see, will it actually do that, right? And these studies are designed as essentially experimental studies, so we'll see. Now, another approach, which is based on the ability to elicit an immune response that we know will work, is can you, in fact, elicit an immune response that gives rise to a neutralizing antibody? That's an antibody that binds to the virus and literally kills it, right? Doesn't kill it, prevents the virus from establishing infection, right? Neutralizes it. Now, we talked about how the virus can change its outer membrane, the outer glycoprotein, very, very rapidly. But there are some places that the virus can't make changes. All right, there's about they've been defined as about 4 or 5 different spots where the virus, if it makes changes, causes a problem. One of the most vulnerable spots is where the virus, what the virus uses on its glycoprotein to actually bind to the CD4 receptor, right? If it can't bind the CD4 receptor, it can't do anything, right? Because it's designed to grow in CD4 positive cells. The virus protects this site, and it protects this site. The reason why I picked the CD4 receptor, the little twerp, is that you usually use a worse name for the virus. Is that the CD4 molecule is a long skinny molecule, so on the glycoprotein surface, it develops this long cleft into which a CD4 molecule can bind, right? It's very difficult for an antibody to get into that cleft, and the virus can play around with the edges of the cleft, all right, to allow it to escape from the antibody response. However, if you isolate antibodies from people who have been infected with the virus for many years, you can actually find antibodies that will bind to that site and neutralize the virus, okay, and neutralize many different variants of the virus because it's not a site that the virus can play around with too much, right, and try to escape. So the trick is, can you develop a vaccine that will give rise to that kind of antibody response? But it's an antibody response that is very much dependent on the immune system of the person living with the virus to have evolved over time, right? These are not antibodies that get picked up right away, okay? A lot of the antibodies that you make to things like flu or if measles are still around, hopefully everybody's getting immunized here, you know, and you make good immune responses to measles and to mumps. The reason why you make those antibody responses very quickly is that your genetic repertoire for antibodies is designed to respond to those viruses. Because those viruses infected you and your ancestors for thousands, if not hundreds of thousands of years, right? But this is a new virus. It's only been around in humans for decades, right? So therefore, your antibody repertoire that's in your genes isn't designed to respond to this virus. So, but the antibody response can endogenously change over time, and it will eventually do that. But a vaccine isn't designed to do that, right? This virus is constantly replicating. So how do you design a vaccine that gives rise to these highly mutated forms of these antibodies? There are ways to potentially do it, right? But this is going to be a long haul, all right? And you can only assess it in a series of iterative clinical studies, okay? So we'll be standing here 6 years from now still having this discussion. At least, I don't know if I will, but we'll meet 6 years from now. All right? No, sorry.
I guess one thing that confuses me about using like neutralizing antibodies as a mechanism is like how do you create something that could be a durable enough response to deal with kind of ongoing virus coming out of reservoir or out of latency?
Well, the concept of the neutralizing, all right, so 2 concepts. So the concept of the neutralizing antibodies to prevent infection.
Oh,
Right.
I'm
But for therapeutic use, that's a whole other story. You know, can an antibody or a combination of antibodies, you know, that have these broad neutralizing capacities be used therapeutically, and will they be effective? I don't know. I mean, literally, so I had the same question you got. You know, it's difficult to, because you're right. What will happen is that the virus constantly will change itself. So you infuse the antibody, it will have an initial response, but then eventually the virus will alter itself, right? So it can no longer respond to it. So in fact, one does see that in clinical studies that have been done. Interesting thing is that there are some early clinical studies that have been reported in the literature in which with the right combination of antibodies, there's a subset of individuals with the antibodies alone in which the virus titer comes down, all right, and then stays down. And even when the antibody goes away, because it naturally turns over, the virus level continues to stay down. Now, it doesn't happen in everybody, it happens in a handful of individuals, but the question is, why is that the case in those individuals? Has there been a resetting of the immune response within the individual living with the virus? Has there been a resetting of that immune response? No one knows yet. But it's interesting to try to figure out what's going on there.
Yeah, I'll have a question.
Right.
So you've mentioned that there's numerous or a number of trials that are trying to find vaccines or other therapies for HIV, but you also mentioned in your talk that in a couple 15 years, 20 years, definitely might get away from us. It seems like there's long ways for a vaccine, you know, the epidemic might be coming, like, right, like, get away from us. How is that all working?
So it's the old story. As you try to develop new biomedical tools, whether it be a vaccine or maybe even a cure, if anybody can figure out how to do it, okay, we've got to do better with the tools that we currently have available, right? So what are they? So as I said, a person who has a fully suppressed virus load as a result of therapy won't transmit the virus, right? So one of So what a very good way to prevent transmission of virus on a population level is to find people who are living with the virus and giving them fully suppressive treatment, right? So we need to do better in that regard, right? We only, we have still tens of millions of individuals to find that are like that. And particularly find the difficult ones, which are predominantly young men who are living with the virus, who have no, men, even in this part of the world, don't access medical services, right? So there's no automatic testing, so you need to go out and you need to find them, okay? So that's one thing that one can do, if we can do that better. And of course, once you do get people in therapy, the 23 million people, 22 million people are currently in therapy, keeping them in therapy for decades and developing systems to do that becomes very important. In terms of developing new biomedical interventions to prevent infection, right? So what do we have? So what are the biomedical interventions? So right now we have oral PrEP, right, which is one pill once a day, but that's tough, right? And it's tough for the reasons we talked about. There are prevention methods that are being developed that are injectable and long-acting. Okay, there are clinical studies to do that. Those will be developed, right? Where it's essentially one injection every 8 to 12 weeks, and you're protected, right? Still, that doesn't mean somebody's going to go get it, right? There are implantables that are being developed, right, which can deliver long-acting drugs to prevent infection that you implant. So think contraceptives, think family planning, same concept, right? You can do the one pill once a day, you can do the long-acting injectable, you can do the long-acting implantable, right? So we can do all of that, okay? But the question is, will they actually be used, right? It's hard on the family planning side, it's going to be even harder on this side, right? And you know what the simplest, easiest, most effective, cheapest biomedical intervention there is to prevent HIV infection? Condoms, all right? It's like, and now you're going to get me started. It's like, blows my mind, all right? When you think about it. Here we are doing all of this stuff, spending an enormous amount of money. For those of you who work in the field, we're paying your salaries, all right? But the reality is we don't have to do any of that, okay? Condoms work, and they work incredibly well, all right? It's the problem. You got to use them all the time, all right? And that's the challenge, and we pretty much know what's going on there. Okay, but that's the easiest, that is by far the easiest thing to do. So.
Your last point about the stagnating global
resource
response, what do you think is needed to get us out of the stagnation?
What's needed is continued political will. Right? So what we're suffering from here, so now you're going to get started on TB. It's not really about, right? So think about it, right? We're talking about HIV, right? TB is worse, right? The numbers of people who die from active TB are almost double the number, almost double, a little bit less numbers that you see for HIV, right? So so here we are focused on all of the resources being thrown against HIV. Why are we not doing it for TB? The reason why, again, it's political will, right? It's really political will, and unfortunately, what happens is that you wind up with what a lot of us call donor fatigue, right? So I'm throwing $6 billion at TB, and I started this in 2004, and I just keep doing it, and I keep doing it, and I keep doing it. All of a sudden, I realize I got to do it for the next 20 years, and I keep doing it. And eventually, these problems tend to recede into the background, okay? And then that's basically it, right? So the big killers are, TB is number 1, actually, right? HIV is number 2, right? And then malaria comes later, okay? But basically, it requires a consistent, first of all, it requires more resources, and even more importantly, a consistent application of those resources, right? Without getting tired. And in fact, that's what you get. You literally get politically tired, right? It no longer sits high in the political agenda.
Right. So TB has the high-level meeting in the UN
Right.
Health Assembly.
Right. 26th, September 26th.
Do you think that's enough?
So the question was, TB has this UN has a high-level meeting on TB, which the objective is to put political focus on TB. Do I think that's enough? No, it's not even close. What the objective there is going to be, if just to get even short-term political focus would be good, but that's got to be translated into something tangible, right? Simply to say it's a big problem and we're all going to work together to do it, it's like me standing up here and saying it's a big problem, we're going to work together to do it. So it's not going to work, right? It's got to be converted into something which is tangible.
I guess I'm thinking alternately we saw in the 90s the effectiveness of
Advocacy.
organizations. Do we think that's where the momentum is going to be for getting political will? Like the top-down approaches
So, political will comes at two different levels. So the question relates to the positive effect that we saw from, the advocates and the advocacy effects, the advocacy events that were going on in the early 1990s and late 1980s. So political will is dependent, first of all, on leadership, right? So you can be top down, but you need a leader. You need somebody to say, this is a problem, we got to do something about it, and this is what we're going to do, okay? Related to it. Right? And we can debate what the motivation point was for George W. Bush to do it, but I remember the day he stood up in front of Congress and said, we're going to do this, right? Everybody around Congress said it's a really good idea. It's still very heavily supported by Congress, right? So guess what? Look at the impact that it's had, okay? So leadership does help. Advocacy is important because, this isn't come as a surprise to everybody, but politicians respond to advocacy. They respond to that. But what's even more important than that, and the primary underlying driver of effective advocacy is accountability. Right? You hold, it's a classic story, right? I'm going to really say something profound here. You hold individuals in power to account, and if they're willing to be held to account, then things happen. The question is, how do you do it? Yeah. So, yeah.
So this is a compliment to Molly's question, but in the case of HIV, one of the things that was so effective was PEPFAR taking this health systems approach
Yes.
and actually building the infrastructure
Yes.
and then providing drug delivery, as well as, I would argue, reaching populations who are status unknown,
Yeah,
such as
yeah.
cervical cancer.
Yeah.
Would an approach like that, or adding a complementary type of entity for TB, be an effective solution?
Yeah, so actually, it's a good, so the question is, PEPFAR, when it gets started, as I mentioned a moment ago, developed an entire infrastructure for delivery of antiretroviral agents and to, not just treat HIV, but also to work around some prevention issues. One thing we didn't talk about is circumcision, right? Voluntary medical male circumcision. That's well known to be to lower the probability of acquiring infection among men, and getting that work through into these populations. TB is practically in every part of the world. Individuals who suffer from active TB, their first primary contact is with the primary healthcare system. Right? So they'll go either to a private provider or to a clinic, but it's a primary healthcare system. So enhancing primary healthcare, right? And that one of the big drivers these days is part of one of the WHO's World Health Organization's focuses over the next few years is universal healthcare, okay, and building the systems to support universal healthcare. That's a heavy lift, right? But related to that, but you build those primary healthcare systems and you build them the right way, okay, then you're going to have an impact on TB. Because one of the biggest drivers of the TB epidemic are what the so-called missing TB cases. So these are cases of individuals who have active TB, but nobody knows them, that they are. Or if you do find them, okay, by the time they actually get diagnosed, it's 4, 5, 6 months later, in which case for 4, 5, 6 months, they've been actually transmitting the infection, right? So it's a, so you have an enormous impact there by building that primary healthcare system. When it comes to HIV, when you really think about it, I mean, PEPFAR had to build this because there weren't really any in these countries. But if you want to make it sustainable and have a really sustainable response, you got to build it into a primary healthcare system as well. So in the end, that's what you need. You need a really functioning primary healthcare system that will work, that will deal with your chronic diseases, that will deal with your vaccination, that will do this, where it no longer becomes a donor-driven, top-down campaign, right? Just like these are. Keep reminding everybody that the E in PEPFAR is emergency. Well, how long does an emergency last? Okay, that's the point. You've got to take it away from something which is an emergency to something which becomes routine. But that means you've got to build that community-based level healthcare system. That's a heavy lift, but that'll get it if you can do that, and that'll deal with TB as well, and malaria, and hypertension, and papillomavirus. Name it all. Anybody, take big. Yes.
What is the risk of development of resistance with non-adherence to PrEP treatment, and is that a consideration in access to treatment?
Not so much for PrEP, right? Because you're not dealing with a very high virus load because you're uninfected, basically, right? So the only chances that would be the case is if in fact you're taking for some reason you become infected, even though you believe you're on PrEP, you may miss it, wind up getting infected, and therefore you'll develop potentially resistance to the 2 drugs that are in PrEP, as a result of the fact that, but you already established the infection. That is very rare. There's been 1 or 2 maybe anecdotal descriptions of that. Whether it's real or not, nobody actually even knows because they're anecdotal, right? But no one's actually ever seen anything. If you run the numbers, you can figure out why that's the case. It's not likely to be an issue.
I was wondering what you can tell us about the various paths to diagnosis that an individual might have who's HIV positive, and is it typically in a sort of a routine screening like you might have with antenatal visits? Is it more often somebody presenting at a clinic that is symptomatic? Is it somebody has a co-infection like TB? What are the kind of most common?
Well, it depends on what parts of the world you're in. So in most countries in the world, is as soon as you make contact with the healthcare system, right? So for any reason whatsoever, right, it becomes almost automatic to screen for HIV. Certainly in the countries that have the high burden, right? So that happens, and that's it. So that's why you find women more than you find men when you look at mortality. That's one of the drivers there, because women have more of an impact, more of an interaction with the healthcare system, whether they go to family planning services. The vast majority of the cases are prenatal care, right? And you do that. But for men, if you can capture them, that's fine. Problem is with men, you got to capture them, right? And because they won't necessarily have that. Now, a new way of doing it, which has been around in this country and in Europe for a long time, but now we've supported a lot of work along with other donors to roll this out in high-burden countries, is HIV self-testing, right? Because one of the challenges that we've learned for anybody is that, particularly for men who are living with the virus, I don't want to be tested by you. I don't want you to know anything, so I don't want to be tested by you. And people don't want to be tested by you because you're a woman, and that doesn't, because I'll get yelled at. And, so seriously. But HIV self-testing, clearly there's a big latent demand there, because as soon as it became available that you could actually do self-testing, and then what you do with the result is up to you, right? Because it's private. All of a sudden those numbers went up substantially, right? So the jury is still out as to what ultimately the yield will be from that, but the latent demand was enormous. As soon as they became available at a reasonable cost that we and other donors, helped to subsidize, the numbers have now grown to about 5-6 million tests within the first couple of years already. So the latent demand was clearly there. So we'll see what happens in that regard. One very nice system that works when you're talking about antenatal care. So you come in as a woman, for antenatal care, you get tested. Unfortunately, be found to, be living with the virus. Is take the kid, bring it home. Or even if you're negative, take the kid, bring it home. And that actually works. Yes, please.
Thanks for your excellent talk. You presented some of the data on the burden of HIV among young women, and then also commented on how there's so much stigma taking what we have now for oral PrEP, which is daily. And I'm wondering if you think that, if you could just comment on the potential and what's in the pipeline for any type of multi-purpose prevention that might vary, birth control that might have a little less stigma within HIV prevention.
So the question related to what we call MPT, or multi-purpose therapies or interventions. So basically, what this is to marry family planning interventions along with HIV prevention interventions. So, for instance, if you could do oral contraceptive along with taking as a single pill, along with taking PrEP. Part of the challenge there is that for these populations in which you have the highest burden of HIV transmission among young women, right, are also populations that don't access family planning services. That's one challenge to begin with. The other challenge is that those populations, as best as we can tell, that do access family planning services, tend to be more often than not your older women, okay, who, if by that time they've not acquired or come across HIV infection, are not likely to do so. Right? So the overlap in populations between where you see uptake in family planning services and where you need to have access to oral PrEP, for example, or isn't exactly the same. Right? So that's part of the challenge that we face. Now, this is not to say that you can't ultimately in the future develop, a combination, particularly injectable or implantable, right? In particular, it's a little bit harder with the oral contraceptives, but an injectable or implantable, where in fact you can have both the contraceptive effect as well as the HIV preventative effect. So it's not off the table. It's clearly on the table. It's on the radar screen to potentially develop them. Whether or not it will have the impact that, at least intuitively, you think it might have, that jury is still out. But we'll see.
Can you talk about how PrEP and other antiviral treatment has affected the prevalence of other STIs? I know that there's some concern about resistant gonorrhea and just generally a rise in other STIs.
No, it's true. Well, so in this part of the world, where there are populations, mostly populations of MSNs living in the big cities, in which oral PrEP is used, fairly commonly, and there are increasing rise in STIs simply because of less use of condoms. Let's face it, right? As a result of it, and there is. But the reality is, I don't know if it was in the popular press a couple of weeks ago. The latest CDC report on STIs in general in this country, irrespective of PrEP, is going up to the roof. It really is, and that's another public health failure, by the way. Okay, is that, and you worry about drug-resistant gonorrhea. You want to scare everybody? Let's face it, drug-resistant gonorrhea. There's only one drug left. One, okay, that can deal with it. Once that goes, you're done. All right, so it's all right, just letting you know. And that's it. Okay, so what is the best biomedical preventative for gonorrhea? Condoms. There you go. I'm going to go to my condoms and vaccine talk next time.
I think we've had a couple of our...
Yeah, sorry.
Did the same sort of mathematical models that show the triple combination therapy might work, looking at viral mutation rates and such, did they suggest in any way that at some point the virus will have a workaround to triple combination therapy?
Not likely to be the case. Depends obviously on what the combination is that you're using. But for those drugs in which the virus can easily become resistant towards, it's the mutation rate is really no more than 1 in 10 to the 4. Okay, and that's simply because, as I said, it's limited by the size of the viral genome. If the number is any more than that, the virus will mutate itself out of existence. So when you think about it, even if it's and the reality is the first triple combination therapy that was used, there was a little bit of an advantage there because for 2 of the drugs, it was a no mutation rate of 1 in 10 to the 4. For the third one, it was 1 in 10 to the 5. So we had an additional tenfold to hit on that end. So no, as long as you keep taking, which is why the development of putting all 3 drugs or 3 different classes of drugs into one pill made all the difference in the world. That really was one of the biggest drivers of having this work. Yes, please.
So, regarding your infections, I was just wondering, how we can, how do I word this question? How do we stress how do we educate people to prevent infections of HIV without raising the stigma around HIV? I feel like this country did a wonderful job around raising the stigma, because I grew up in West Africa and HIV was such a big deal. You date someone before anything, you have to show your test and everything. And then when I moved here, there was no talk about HIV. So I felt, to me, it was what is the burden of HIV in the U.S.? And then I started working in public health in a jail setting, and it was really amazing because a lot of these young people saw HIV as a chronic issue. They didn't really take it seriously. You would try to educate them and their partners, and it was well, it's just like diabetes. I can just take my pills and it'll be fine.
Well, you see the concept of HIV as being something that you can deal with as a chronic disease. You see it even in populations in Southern Africa, right? I've spoken with young women there who say, well, it's not a problem. You get it and you get there. But the stigma, particularly in the rural high incidence communities, as you probably know, in that part of the world is still very high. HIV is there. You know it's there. Everybody recognizes it's within the community. Everybody knows the people who go to the clinics to get their drugs, related to that. But you don't talk about it. And part of it is driven by very conservative sexual mores, right? How are you going to get HIV? You're going to get it because you're sexually active. Well, you shouldn't be sexually active. I don't want anybody to know I'm sexually active, right? It's the same problem, right? So it's how you begin to deal with that. So one of the big efforts that we and others are doing is really trying to understand, and this gets to the point you were trying to make, is we're really trying to get to understand where at a community-based level, this becomes something acceptable. It becomes acceptable to talk about HIV. It becomes acceptable to try to protect yourself against HIV. It becomes acceptable as almost a community obligation that this is something which you need to do. Okay? And that's not easy, obviously. Okay? Certainly not in conservative societies, but it's what's going to be needed, right? Because if you don't talk about it, you're not going to try to do anything about it, or you're going to try to avoid it, even though you know it's there. That's the thing, the same thing you just said. That's the thing, you know it's there. And you know it's in the environment, and you know other people who've had it, but I won't talk about it. That's one of the big challenges.
How do you help these young people here in the U.S. to protect themselves?
Well, here in the U.S., you have populations in which that kind of stigmatization occurs, right? Mostly among Black MSMs, right? And that's well known, right? Among Black MSMs, first of all, being an MSM in a Black population, as you know, is not very acceptable, right? So you've got that issue that's associated with it, and that these, unfortunately, are marginalized populations in which public health services don't always get to them, right? And we see them. I mean, there are some states in this country, and I won't name them, where the situation in those populations is as bad as anything I just described in Southern Africa. You can pretty much figure out where they are. Yes, please.
Something that stuck with me through your presentation is that you said that what rendered this virus the ability to evade the immune system was a mere combination, rare random combination of genes. And I am thinking about infectious diseases and how we found cures for, you started talking about polio, and we had all the vaccines, etc. We hear a lot about HIV, and I am thinking there were viruses in Egyptian mummies, and viruses have always existed. So why in 2,000 plus years we find this random virus that was able to evade the immune system, and we talk so much about it, and you said it was a mere rare event. That rare event could have happened millions of times.
You're absolutely right. All right, so let's talk a little bit about that. First of all, that recombination event I was referring to was not to help the virus evade the immune system. It was to allow the virus to actually infect cells, okay, of great apes, right? So this is a class of viruses that clearly has infected primates, small primates, monkeys, for thousands, if not hundreds of thousands of years. Great apes, which include gorillas, chimpanzees, and bonobos and orangutans and humans. There are only 5 species of great apes and subspecies. These viruses could not infect. And one of the reasons why is that there are, in fact, molecular checkpoints in the cells of all of the great apes that prevent this particular class of retroviruses from infecting the cell. Right? That's an interesting, fascinating story all by itself. This recombination event, if you will, that occurred, essentially allowed the development of a virus, so permitted the virus to develop, to express multiple molecular mechanisms that the virus had to evade all of the molecular checkpoints in the cells of great ape. Right? So the recombination event, you're right, may not have been rare, okay, because I'm assuming there's more than one chimpanzee that's eating different species of monkeys at the same time. So the recombination event was not necessarily rare. What was rare was the fact that you had the establishment of the infection in that animal that then probably transmitted to other animals, right? And there could be a number of different reasons, related to that. The fascinating thing about it is retroviruses. If you look in your genome right now, you will find what are called transposable elements. Transposable elements are, some people refer to them as jumping genes. Okay, so what these are the archaeological remnants of retroviruses that infected your ancestors, maybe even before they became humans, way back. All right, literally eons ago. Okay, and they're still in there with you. Okay, and then that's it. This belongs to that particular class of viruses, but retroviruses, that establish those genetic sort of archaeological footprints in the human genome are actually not particularly good for you. They cause mutations, they cause all sorts of problems. So over the eons, again, humans and related species developed molecular inhibitors within cells that would prevent these viruses from establishing infection. And what happened here, by a chance event, you wound up with a virus that could evade all of those molecular inhibitors.
Can I ask a second part?
Of course.
Okay, the second part of this is we hear a lot about AIDS and HIV, and we're thinking, the so-called infectious, but do you think that as we learn more about cancer, we would know that it was not only in HIV, but all these cancers that are associated with viruses are also under the same effect, that we can't do anything about it because of the peculiarity of the virus?
No. The reality is, a virus that is probably one of the most significant viruses that subsequent to infection results in cancer is cervical carcinoma and papillomavirus. We can prevent papillomavirus infections and therefore completely prevent cervical carcinoma development, right? So it is doable if you know that the virus is responsible for it. Hepatitis B virus, right, that causes hepatocellular carcinoma, and people who become chronically infected with hepatitis B virus. You can prevent that. Probably everybody in this room is hepatitis B immunized, I hope. So you've got, so you can do it. So there are a number of cancers that in fact are associated with, as a result of virus infections, for which there are successful vaccines that have been developed to prevent them. Now, there are a lot of cancers that have nothing to do with virus infections, right, that develop, right? Kaposi's sarcoma that I was talking about a little bit earlier, that is actually caused by a virus. That's actually caused by what's called human herpes virus 8, that, by the way, was discovered by Bob Gallo, that in fact is responsible for that Kaposi's sarcoma. That the immune system naturally keeps under control unless you wind up with immunodeficiency and it allows it to balloon out. So, so they're there. But if you can clearly identify them and clearly show that association is there, you can prevent it. Again, papillomavirus and cervical carcinoma is the classic example. Hepatitis B, the same story.
So I think we will go for one more question. I know that I can probably ask more and more questions throughout the night, but we probably should limit ourselves. So if we have one last question for the evening.
So I have a comment and a question. So you were just talking about stigma in different parts of the world. In the past 10 years, I have seen there's an explosion of movies in India and Pakistan where good guys are shown as suffering from the virus AIDS.
Yeah.
So it has made a very, very big difference in just 10 years.
Yeah.
So the other thing is, thanks, very nice talk today. This is really appreciated. How optimistic you are about the development of vaccine and how satisfied you are with the resources being spent on that?
Both questions before, it gets a point where you work on things so long you become agnostic, right? So how optimistic I am? So let me put it to you this way: we still work on it, okay? So does that, and simply because it's driven by the fact that, in the end, if a vaccine can be successfully developed, it will have probably one of the biggest positive epidemiological impacts. That's true for any vaccine. So therefore, we'll see basically, what happens. And again, we've been talking about the resource questions all along. It still needs more resources. It needs more R&D resources. It needs more resources to deal with the social issues that we talked about and all the delivery issues that we talked about as well. Okay, great. Okay, well, thank you very much.
So I want to say thank you once again for everybody for joining us tonight, and that's going to be this.
right.
Okay. For this wonderful talk that he gave. We have just a few minutes that if you want to come up and have a small bit of chat with him, please do so. But also, please remember that the Global Health Series is every second Tuesday of every month for well into the end of 2019. So I'm just setting up that schedule right now. And I encourage you to come back every single time. These questions that you guys are asking sometimes are actually answered by other researchers that we have listed here. So I hope to see you all back. Thank you.